Am I audible? Am I audible? Hi, so welcome to the fifth live session of Algebra 1. So first let me introduce myself. My name is Shautik and I am doing research on data economics, cost and income and academic measurements. So today in this live session, we shall go through some group action related things and then Shiloh theorem. I mean, that is my plan. But since this live session is mainly for problem solving, so without any hesitation, kindly ask any doubt or any confusion if you have. Okay, please ask me your doubts whenever or any confusion. You gotta stop me and ask by unmuting yourself. Okay, so first let me know. Okay, so let's start with. So yeah, so we all know group actions. In the second and third live session, I've discussed this, right? So today, first let's start with the following problem. Let G be a finite group of order n order. Then G is not sim, G is not a simple group. Okay. So the question is that, hi, can you, am I audible? Please let me know. Am I audible? Is this screen visible to you? Please let me know. Okay. Okay. So first, okay. So if you have any question or any doubt, please ask me. Okay. Because this session is for the problem solving session. Okay. So please unmute yourself and ask me whenever you have any doubt, any confusion, or any question. It, I mean, though it may not be related to previous session, but you can ask any questions related to the syllabus or what you have done in the search class. Okay. So today, first we are starting with the following problem. Suppose G is a finite group of order 2n and n is an odd number. Yeah. Then we need to show that G is not a simple group. So how to do this? So for this, we need to use the I mean, this problem can be solved in two ways. One can use Euler's theorem, and another way is directly using the group action. But the using group action is more fundamental. That's why we solve this problem by using the group action. by choosing a particular action. So consider the action psi from G cross G to G x comma G, sorry, G comma x goes to Gx. It is an action. Okay. Now observe one thing, that it's an action. Observe one thing, order of G is equal to 2n, which is an even number. So this implies what? This implies G has an element of even order, right? Sorry, G has an element of order. Call this order 2 element some x1. Okay. Now consider this map tau x1 from G to G. G goes to x1 G. Okay. And since order G is equal to x1 G, I mean order of x1 is 2, so x1 G, it's tau x1 is equal to G. So now we know that for a group action, this gives a map from A to G, sorry, a G to collection of bijection from G to G, that is G to tau G. It's an group homomorphism. Now point is that observe that, so consider the, so x1 goes to tau x1. Okay. Now observe that since tau x1 of any G is x1 G, and tau x1 of that x1 G is equal to G. So this implies this permutation tau G is of the form G comma x1 G, that is a 2 cycle. Okay. Now, so we have a map from G to or G, sorry, G to collection of bijection from G to G, AG. And from AG to we have a map from plus minus 1, where the sigma goes to 1 if sigma even permutation, goes to minus 1 if sigma odd permutation. But since tau x1 is a 2 cycle, so tau x1 is an odd permutation. So this composition is an surjective. If we call this composition capital F, so capital surjective. So some G by its kernel isomorphic to Z2. So this implies kernel F is a non-trivial normal subgroup of G. So that's why any group, so I mean, so this tells that G is not normal. This tells the group order 2 and A naught is not normal. Yeah. So this is the whole solution. So okay, so first let me repeat what we have done so far. So the question as follows: so G is a given finite or 2n, and it is odd. We need to check that G is not simple. Okay. So this can be done by using Shaila theorem, but also it can be done by using group action. But I feel that using group action, the solution seems to be more fundamental. That's why we have solved this problem by only using group action. So in order to use the group action, we first pick some action. So fix an action psi from G cross G to G. The translation map G comma X goes to Gx. Now, so order of G is equal to which is an even number. So G has an element of order 2 because any group order must have even number. Call that order 2 element to be x1. Now, for any action, we can associate a permutation tau x1 G goes to x1 G. So tau x1 of x1 G is equal to G. Now, G to AG, it's a group homomorphism because psi is an action. That is G goes to tau G. Now, the point is that, so under this map, x1 goes to tau x1 and tau x1 of G is equal to x1 G, but tau x1 x1 G is equal to G. This implies tau x1 is equal to G comma x1 G, which is a two cycle, right? So it's an odd permutation. Now we are considering the whole composition G to AG and AG to plus minus 1. Where this AG to plus minus 1 map is sigma goes to 1 is sigma permutation, it goes to minus 1 is sigma odd permutation. Now the whole composition will be surjective because the map tau is the odd permutation and identity is the even permutation. I mean, this goes to even permutation. So G by kernel isomorphic to Z. So that's a kernel isomorphic. It's normal to G. Okay. This is the technique. I mean, this is the solution. Please let me know if you have any doubt or any confusion or any part you could not understand properly. Please ask. Any doubt or confusion, please ask. Okay. So this time you don't have any question, but anyway, if you have any doubt later, please ask. Okay. So what is the application? So it is some easy applications are like obvious. Of order 30 not simple. So one more thing is that here we got G is normal in the previous problem with a normal subgroup of order n. This is the another it's a fact that any group of order 2n in is odd must have normal sub order n. So group order 30 is not simple. So same why? Because 30 is 2 into 15. 15 was number, so that's why it must be a subgroup of order 15 which is normal. Okay. So okay. So so this one thing. Okay, the same thing is there is something known as extended Kelly theorem. So how many of you heard about extended Kelly theorem? How many of you heard about extended Kelly theorem? How many of you heard about extended Kelly theorem? Please reply in the chat or please unmute yourself and let me know. Okay, it seems that everybody knows the extended. Okay, so anyway, first let me state the Kelly theorem. Then we shall see some examples. Okay. So what is the statement? Also, some of you might be in MSc, maybe in MSc, or some of you might be in this third year. But the thing is, in upcoming MSc entrance or PhD entrance, for those who are interested to do it, actually, this extended theory is actually very useful. Like many problems of group theory regarding the having normal sub or not can directly solved by actually using this Cayley theorem. Okay, I mean Shiloh theorem is a good tool, but Cayley theorem is a clever tool. So you should remember the statement and you need to understand how to apply this theorem. Okay. So the statement goes as follows. Suppose G is a group and supposedly GB group and suppose H is a group of G. Let the index of H in G is equal to n. Then there exists a map F from G to Sn such that kernel of F is contained in H. So this is the Kelly's theorem that G is a group, extended Kelly G is a group. H is any subgroup of G if the index of H in G is n, then we can find a homomorphism. I mean, there is a F obviously a homomorphism. Kernel of a subset of H. Okay, so this is the thing. So so one application. First, let's see.
Sir, please scroll down the page.
Yes.
Uh,
Okay. It's fine.
Hello.
Yes, is this fine? Or should I
Yes,
go?
still. Okay, okay.
Oh, okay. So yeah. So the statement goes as follows. Suppose G is a group and yes, and H is subgroup of G.
Sir, today have you solved any? Sir, today
Yes,
have
yes,
you
yes,
solved any? Have you solved any assignment problem or other kind of problem? Just
yes,
now.
yes. First we have discussed one problem. Suppose G is a finite group ordered to n. For n is ordered, then G is not a simple group. So first we have discussed this problem. So yeah, this is the first problem we have discussed. Yeah, I mean this is the only one problem we have discussed before the extended Kelly theorem. Okay. If you ask me, then I will repeat this first problem. If you ask, then I will repeat this first problem. Okay. So okay. So application is as follows. Suppose G is a group of order 15. Okay. We show we will show G not normal by using the extended Kelly theorem. Okay. in order to use the extended Cayley theorem, we first need to come up with some subgroup, right? Now 15 is equal to 3 into 5. Okay. So by Silas' first theorem, we can choose a Shiloh 5 subgroup, call it H. Then what about the index of H in G? 3. Okay. So the extended case, we must have a homomorphism. Yeah. From G to S3 such that kernel of F is contained in H. Okay. Now, if kernel of F is equal to 0, I mean this kernel of F can be 0 because if kernel of F is equal to 0, then G lies inside S3, right? But order G is 50, so G can't lie inside S3 at least. So kernel of G is non-trivial. So this implies kernel F is a non-trivial normal subgroup of G. So yeah. So this is one application of phrase type. Okay, so first let me repeat what we have done. Suppose this is a group order 15. Our target is to show that this is not normal. So we shall try to use the extended Cayley theorem for this. So for this, first we need to construct a Shiloh 5 subgroup. So let it be H, and the index of G in H is equal to 3. So then we can find a homomorphism F from G to S3 so the kernel of F is contained in H. Now if kernel of F equal to 0, I mean now the kernel of F can't be equal to 0 because if kernel of F is equal to 0, then G lies inside S3, but it's possible because order of G is 15, order of S3 is equal to 6.
Hello, sir. Why kernel is equal to 0 not possible? This logic is not clear to me yet.
The kernel equal to 0, this means what? This means G
Injective.
lies, yes, F is injective, that's why G lies, I mean, now if F is injective and F G is a subgroup of S3, right?
Yes, sir.
Correct? So order of Fg will divide order of S3, which is 6, correct?
Mm-hmm.
Now order of G is 15, right? So order of Fg will be 15. So 15 divided 6. That's not possible, right?
Possible, not possible.
Yeah, that's why kernel of F should be not 0. And kernel of F is anyway normal. So that's why it has a non-zero normal subgroup. Okay. So this is the advantage of Cayley theorem. Of course, it can also be done using the Silas theorem. But yeah, Cayley theorem makes it a little smaller. So that's the point. So does everybody understand this solution? Does everybody understand the solution? Okay. So the next problem is that G is a group and H is a subgroup of G. Let order of G does not divide G is to H factorial. Then H is, then G is not normal. G is a group and H is a subgroup of G. So the order of G does not divide G to H factorial. We need to check this on normal. Try to do it using extended Kelly theorem. Please try to solve this by the extended Kelly theorem. I shall get back after 2 or 3 minutes. Okay, so anybody had done this problem which written on screen? Anybody please? Okay, so this problem is direct application of extended Kelly theorem. As follows. So by extended Kelly theorem, we will get a homomorphism. So assume G is to assume G is to H is equal okay. get a homomorphism F from G to Sn such that kernel of F is contained inside H. Now, if kernel of F equal to 0, this implies order of G divides factorial N, right? Which is nothing but G is to H factorial. So if kernel is equal to 0, then order of G divides G is to H factorial. But the given condition is the order of G can't divide this. This implies what? Guys, kernel of F is strictly greater than, this implies kernel of F is a non-zero. And anyway, kernel is a normal servo, that's why G is not simple. So it is non-trivial. So G not simple. Okay. So this is another application case. So please let me know. Till now, do you have any doubt or any confusions? Please ask.
Hello, sir. Order of G divide n factorial up to that point here. All right. Then uh, in given G not divide.
Yeah. G, given that G does not divide G is to H, G is to H factorial. So that is why kernel, now if kernel equal to 0, then obviously order G divides G is to H factorial. That's why kernel can't be 0, right? So kernel is a non-trivial subgroup of G, and kernel is always normal. So that's why G can't be simple.
Yes, sir.
Okay, so this is so so okay, so consider for a problem. Let G be a group and H a subgroup of G. And let G is to H is smallest prime dividing order of G. So show that H is normal G. So what is the question? The question is that suppose H is a subgroup of G, and given that G is to H is the smallest prime dividing the order of G, then show that H is normal subgroup of G. This can also be done, but this can be done by using extended Clay theorem. So first you try, then I will do if you can't solve the problem. So please take your time and try to solve this. Remember, if somehow, H is given, G is to H already given, so you need to make use the Clay theorem. Okay, please try.
Sir, please one question. Just this is not relevant to this problem.
Yes.
On the date, on the previous, just previous session, today's previous session was hold on 21 first August.
Uh, 21st was a Monday, right?
Mm.
Okay, that was taken by some other person, right?
Oh, I have up to which I have remembered last class you'd end at the point of direct semi-direct product and some application of grow class equation.
Yes, yes, right, correct.
After that you have not taken at all, right?
Yes, right. This is the next class.
ठीक.
Maybe there is nothing.
Okay.
Okay, let's try this problem. Let us run on screen. So does anybody?
Sir, it has, this is smallest prime means the G quotient H cardinality is 2.
I mean, in the order of G, if we consider prime factorization, then there must be the smallest prime, right?
Oh,
In the
it is not
factorization.
necessary the 2. 2 is not necessary.
Reason the G is to H is the smallest prime dividing order of G. I mean, so obviously it may not be 2, right?
Uh,
Anybody solve this problem or any idea how to proceed? At least attempt to solve this. Okay, sorry for the inconvenience caused. In between my internet connection lost. That's why uh, now it is not. Now actually, I'm trying to connect, but it was not connected. Okay, sorry. Okay. Okay, so the solution is as follows. That sorry, that's coming. Yeah, okay. Hi, am I audible?
Yes.
Maybe because suddenly it's will internet when due to the connection internet. That's why. Sorry about that. Just okay. So in meanwhile, anybody tried this problem? Anybody?
Go- Trying till now, trying.
Sorry, I didn't get. What the I didn't get you explain. I could not hear about it. Okay, so yeah, you okay, so you told that you are trying. So in how I mean what is your approach? Can you please explain us in brief? What is your approach?
It is
Please tell me.
G quotient each order of the G quotient each is prime number. So
Yes.
so extended Calais theorem, according to extended Calais theorem, there exists homomorphism from G to S P, where P is prime.
Yes.
Mm,
With kernel of
and
F is contained inside it, right?
kernel of
Then
kernel of H.
what you are trying to do. Okay, so firstly, we already know the kernel subgroup kernel is normal. It is we already know, right? Now we need to check.
Yes.
Now the question tells us to check whether age is normal. So one obvious
Mm,
way to check that kernel is equal to full age. If we can show this, then age is normal in G, right? Correct?
correct.
Yeah. So basically, by I mean somehow we need to show actually that kernel of f is actually equal to x. This is the main thing we need to understand.
Mm,
Yeah. So for this we need to use again the smallest prime thing somehow. Now can you please try how to do this?
mm, yes.
Please think about it. Others please also think about this problem. Our main target is to show the kernel is equal to base. Okay. Somehow we need to prove this. Okay. How? Please think about it. By the way, this is my
Sir, can we proceed contradictory way?
yes, sure, sure.
Suppose
So
kernel F, order of kernel F must divide order of G. So, if the order of kernel less than order of h,
Yes.
and least prime given is it must be least prime. So
Yes. Then. Yeah. Then. Least prime is a G is to H least prime, right? So that is order G by order H. This is the least prime dividing the order of G, correct? Right?
right.
Yeah. So somehow you need to go with quotient. So idea, one way is to do the quotient. I mean the factor, since G to SP is the map with the kernel F. So G by order of kernel F. This should be by order of SP, the SP factor, right? This is one way you can think about, correct?
Yes.
Yeah. Now from
Yes.
here, try to show that kernel of F equal to whole of H.
Mm.
That's right. Any other? Except him, any other is trying some other way. We somehow need to use the fact that G is the smallest prime. By using the fact that order of G by kernel F requires factorial P. Somehow need to, from this somehow we need to come up with G by H. Okay, let's think about it. Okay, so let me. So okay, so So order of g by kernel phi is equal to, I mean, it's multiplied with some t is equal to factorial. Okay. This is what, this is order of g h factorial, right? And g by kernel phi can be written as order of g by h in the order of h by kernel, correct? So order of h by kernel f into t is equal to p minus 1 factorial, right? That is p minus 1, p minus 2, that 2 dot 1. Okay, this is the thing. Now, if kernel f is proper subset of h, this implies what? Order of h by kernel f is a number which is greater than 1. This implies this had a prime divisor, call it p prime. Now consider this equation. This implies what? I mean,
Sir, your voice is cutting.
okay,
Maybe it's my side problem or your
no, it's actually
network
my
issue.
production that I'm turning off my camera.
Your voice cutting discrete.
Okay, now is it fine?
Uh,
Now it,
it is visible whatever you are writing on the board, but I cannot hear properly. Uh, Please continue in writing. Go.
okay,
Yes, maybe network issue.
okay. So the thing is, okay. So let me write it again. So g by kernel f divides factorial p. Okay. So this implies what? Factorial p is equal to some t multiplied by g by kernel f. Okay. This can be written as follows: p into g by h into h by kernel f. G by h is equal to p. So this equation tells p minus 1 factorial equal to t into order of h, the order of kernel f. Okay. Now, if order of, I mean, if kernel f is a proper subset of h, this implies I don't know why there is an internet problem right now. I'm very sorry for this. Okay, so yeah. So can you see the screen right now?
The screen and hear properly.
Okay, so if kernel of A is a proper subgroup of H, this implies order of H by order of kernel F. This is a number which is greater than 1. So this will have a prime device. Call it P prime. Okay. This implies, and this equation implies this prime divisor P prime divides P minus 1 factorial. Sorry. So this prime is a p prime is strictly less than. Sorry, this implies that prime is a p prime is strictly less than p. Okay. So this implies um, now what is p prime? P prime is a prime divisor of uh, order of h by kernel, right? So this is my p prime is a prime divisor of order of g. Okay. So p prime is a prime divisor order of g, and p prime is less than p. Sorry, p prime is less than p. So it's a contradiction of the fact that g is to h the smallest prime dividing the order of g. Okay. So this is the full argument. But since there's some disruption, so first let me repeat the argument again. So argument was as follows. Argument was as follows. So given that g is to h the smallest prime dividing the order of g. Okay. So and we need to check h is normal. So first we use the Kelly's theorem. So we will find that we have a map f from g to xp with kernel of f subset of h. Now we will show the kernel of f is equal to h. This is what we will show. Now, so okay, so the technique goes as follows. Since so g by kernel f is ordered divides factorial. So we can write g by kernel f is equal to g by kernel f is g by order of h, order of h, order of h. Okay. Now g by h is equal to p also. So order of h by kernel f into p is equal to p minus 1 factorial. This is equal to p minus 1 dot to p minus 1 dot 2 into 1. Okay. Now our target is to show that kernel is equal to h is the target. So assume on contrary that order of kernel is the proper subset by h. So order of h by kernel is greater than 1. So this order of h by kernel has a prime divisor called it p prime. Okay. Now this equation tells that call it p prime. Okay. Now this equation tells that p prime divides factorial p minus 1. Now since p prime is a prime, so whatever in the right side the prime factors of p minus 1 factorial are less than p, right? So anyway, p prime is strictly less than small p. Also p prime is a prime divisor of h by kernel f. So p prime is a prime divisor of g. So we get a prime divisor of g which is strictly less than p. So yeah, so that's why so this is the contradiction because g to is given to the smallest prime dividing order of g. So that's why kernel of f has to be equal to this. This is the technique. This is the solution. Okay. Does everyone understand the solution?
Yes, yes.
Okay. So okay. Wait for 2 minutes. Let's get back. Okay. So one application goes as follows. Suppose G is the group with order of G, P1, P2, P3. Okay. I mean, obviously P1, P2, P3 are primes, and P1 less than P2 less than P3. So any subgroup of order P2, P3 is normal. Okay, this is one application concept. Similarly, also G is the group order G is P to the power n. Then any subgroup of order P to the power n minus 1 is normal. Okay. Yeah. So these are some small applications. So yeah. Okay. So yeah, that's fine. Yeah, that's all what you can get from there. Okay. So now okay. So now let me start the Cauchy theorem first.
Sir, kindly bring down, please. Once I have not written yet. Uh, Last line, what is written? The, then any subgroup of order p to the power n minus 1 normally in G.
Uh, yes, right.
Yes, yes, I have written. You can go further.
So so in a yeah. So next. Okay. So next, we shall first start with the something Cauchy theorem. Okay. So the statement goes as follows. Suppose these, I mean, GBA group and P prime dividing order of G. This implies we have existed element G in G order. Sorry, there is an element G. There is an element order T, hence G as a subgroup of order Q. What? I mean, this is what the Cauchy theorem says. So the thing is, if a prime is order of G, then we can, there must exist elements of the same order, and so obviously the subgroup generated by that element will be of order Q. So, for example, I mean, what is the application? So try to solve that any of order 10 must be 1. Yeah, okay. So any commutative group of order 10 must be cyclic. That's right. Using Cauchy theorem, show that any commutative group of order 10 must be cyclic. Okay. Let's try. Can is only found out by using Cauchy theorem. Let's take a time and think about it.
Sir, bring down the page. Bring down the page slightly. And see as a subgroup of order. Okay, right. Sir, it is 10, 5 into 2 is equal to 10, corresponding to 5. There was a 5 is prime, obviously, corresponding to it is has a cyclic subgroup order 5, and 2 also is prime.
Uh-huh.
It also, hello.
You have said prime is, so prime is there. Then what else I could not earlier. After the prime, what would
I
say?
have not here. I'm saying 10, 10 composed of 5, 5 into 2, corresponding 5, there was a cyclic subgroup, and corresponding to there was also a prime cyclic subgroup, and they are also normal, and they have common only identity element. So the given group of order 10 is yeah, isomorphic to group of order 5 cross group of order 2, and this is also cyclic becomes.
Right. Yes, very good. You're right. Okay, so let me think the next one. Okay, so yeah, so you all know about Shiloh first, second, and third theorem, right? So everyone knows this, I think. Okay, so uh, there is a one fact is that suppose this is a group and order of J is equal to PQ. Let P greater than Q and PQ are primes. Obviously distinct. Okay. And let P, let Q does not divide P minus 1. Then G is cyclic. So the question is follows. Suppose G is a group of order PQ and suppose P is less than Q, PQ primes, and let Q does not divide P minus 1, then G is cyclic. Okay. Have you solved this problem before? Have you solved this problem before? Okay, please respond. Okay. So, another fact is that if Q divides P minus 1, then there exists unique non-abelian of order 10 of order PQ is isomorphic with each. Possibly on next we shall try to attend this, but today for the first portion G is given PQ and suppose Q does not P minus 1, then G cyclic. Please try to solve this problem using Seiler theorem. And the Q divides P minus 1 case can be done by using the semi-direct product. So we shall go through this in the next live session. Next slide. Let's try the first part that if Q does not have P minus 1. Sorry, I've done this mistakenly.
Sir, a fact it is associated with the first part of the question.
No, not first part is that G is a PQ and P less than Q. Okay,
Mm.
PQ primes. So the first condition is that if P does not divide Q minus 1, then G is cyclic.
Mm.
But if P divides Q minus 1, then G is isomorphic to a non-abelian group. Understand?
Okay, okay.
You need to use the Silo theorem. Just try to solve it. And just try to make an attempt. So anybody got the answer? Or anybody or any idea? And then okay. So let's see how to solve this. For the first part, so order of G is equal to PQ, right? So what are the factors? 1, P, Q, PQ. Let NP be the number of child of P subgroup. Then NP divides order of G. So NP divides either 1 or P or Q or Q, okay? But P is less than Q, correct? So, I mean, also NP is equal to Kp plus 1, okay?
Mm,
Now,
yes.
Kp, yes, any question, Kristen? Any question, Kristen? Okay, now NP is Kp plus 1, right? Now if Kp plus 1 divides order of G, so Kp plus 1 has to be either 1 or P or Q, right? But Kp plus 1 can't be 1, I mean Kp plus 1 can't be P because it's Kp plus 1. Okay. Kp plus 1 Q then is in what? P divides Q minus 1, but this is not the case because it is already given that P does not have Q minus 1. Now Kp plus 1, can it be PQ? No, it cannot be q because the right side is divisible by p, but the left side is divisible is not divisible by p. So that's why np, the number of side of p subgroup, is 1, and it is easily can be checked that number of Shiloh q subgroups is also 1. Okay, so number of Shiloh p, number of Shiloh q also 1. So they both are normal subgroups, right? Okay. Call this to be H in Shiloh p and call this Shiloh q to be K. So H and K cyclic, and the normal subgroup of the intersection is also 1. So this implies G is equal to HK, which is isomorphic to HZK when H cross K. And H is equal to ZP, K is equal to ZQ. So this is same as ZPQ, which is PQ is equal to 1. Okay. So G is isomorphic to ZPQ. So I mean, yeah, that's why G is cyclic. So this is argument. So first let's focus on it very big first. So what I've done, so G is any given group out of PQ, and suppose 1 divides P divides, and NP is the number of Shiloh P subgroup, NQ is the number of Shiloh Q subgroups. Okay. So and NP is equal to KP plus 1. Okay. So KP plus 1 will be equal to either 1 or P or P for Q. Now KP plus 1, can it be 1? It may be, but can it be P? No, because P does not divide KP plus 1. KP plus 1 can't divide Q because if KP plus 1 equal to Q, then P divides Q minus 1. That is not the case because in the question is given that P does not divide Q minus 1, right? And KP plus 1 can't be equal to PQ because KP plus 1 is not divisible by P, but PQ is divisible by P. Okay, so KP plus 1 equal to 1. So number of Shiloh Q subgroups is 1. Similarly, number of Shiloh Q subgroups is also 1. So both are normal subgroup, and obviously PQ prime says the intersection is 1. So HK is isomorphic to H cross K, which is nothing but ZPQ. So that's a G cycle. Does everybody understand this argument?
Yes, clearly.
What about others? Okay, I shall wait for some minutes. Please let me know if you are in doubt or confusion, then we shall move on to the next question. Okay, so the solution is clickable. Okay, so let's move on to the next question. So, can a group, oh sorry, can a group order 77 normal? So the question. So can a group order
Sir,
77?
the second part of the previous question, is it left as exercise?
No, 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 no. We will solve it in the next step.
We solve in next class.
Yes, yes.
Okay, okay.
Okay, so the next question is that can a group order 77 be normal? Think about it. Sorry, it's simple. Sorry. Can a group order 77 be simple? Sorry. As a group of order 77 or the simple? Think about it. 77 order group may be simple, may not be. Think about it. This problem can be solved by, I mean, this question can be solved by using whatever we have done in this previous session. There is this thing, stay tuned and listen. Yeah. Does the group order 7 always simple? Anybody? This can be solved
Sir,
by
it is a 77. So 77, 7 divide 77, 11 divide 77. Both of them prime. Both of them prime. So say,
you are in the right track.
hmm?
You are in the right track. You are in the right track. So then, 7. Then what to do?
Seven group of seven science cyclic subgroup and 11 also cyclic subgroup. Order of prime
Right.
order. Prime order.
Yes, obviously cyclic subs. Yes, right, correct. Then,
Simple means there are only trivial normal subgroup, no non-trivial subgroup, but they're available.
right. No, no, 7 order group cyclic. That is correct. So, but 7 order group inside some other group. So when it belongs to inside some other group, it may be cyclic, may not be cyclic, right? So you need to check that It is normal, firstly. So how to check, or it is not normal, how to check? Just go to the last uh, question.
Uh, Last question solve. मतलब
Just look at the screen, right?
7 does not divide 10. 7 does not divide 10. So
So 77 group is always cyclic, right?
uh,
So it is not simple. I mean, it can be simple, correct? So so is the group of order 36 simple? Group of order 36 is simple. Let's take a, it can also be done by using only this thing. Okay. So this is the thing. So just
one question. If
yes,
we somehow if we come to conclusion that any group has a unique silo p subgroup, then it must be normal.
yes, right.
So three, yes, yes, 2 plus 2 square into 3 square. So,
Okay, so For this, we need to use. Okay, so first let me get that. Use that extended Kelly theorem. Now try to solve this. Okay, so let me do. So take H. I mean 2 square and 3 square, right? So choose a subgroup H such that order of H equal to 3 square by the Schiller theorem. So then what about G is to H? G is to H is equal to 4. So there is a function group homomorphism F from G to V as 4 such that kernel of F is contained inside H. Now what is this 4? What is 4 factorial? 4 factorial 4? 4 into 3 into 2. 12, 24. Okay. Now if kernel of, now obviously, kernel of F equal to 0 implies order of G, the order of S4, but this is not possible. So kernel of F is non-zero. So this implies kernel of F is non-trivial. It's a non-trivial normal subgroup inside G. Yeah, that's the argument.
Okay.
You understand?
Hmm.
Okay, so it can be done using Schiller theorem, but let's not get into this. Yeah, almost similar it can. So, okay. Okay, so you know the class equations, right? So can anyone tell what is the class equation of S3? Anybody? Can you tell the class equation S3? Anybody? Please. Shayantan, please. Let me know. So what is order? The order of S3 is 6, and what is order is that is 1, right? So 6 equal to 1 plus something. So, and whatever the something, it should divide 6, right? So only possible way is 2 plus 3. So this is the classification for S3. Understand? and basically this is the conjugacy class of 1 2 3. Yeah, 1 2 1 2. This is the conjugacy class of 1 2. So that's the point. Do you understand? I mean, the
Yes.
point is how to calculate classification without actually calculating it. In case of S3, left side 6 and 1, and for the other portion, we need to fill it out in such a way that it should divide 6. So only possibility is 2 plus 3. Okay? That's it. So, what is the class equation of Q8? Yeah. What is the class equation of Q8? So look, in Q8, it's it has order 2, right? Sorry, center is the order 2, correct? Okay. Now, what about the other elements? That is, what is the class of I? Class of I can be thought as order of G by order of centralizer of I. Okay. Now, I, the element I is not in the center. So, its centralizer strictly contains its center. U8 is order of 8 and order of center is 2. So, order of centralizer is only 4, because if order of centralizer is 8, then I should belongs to center. So centralized order 4. This implies what? That order of conjugacy class is 2. So only possibility is 2 plus 2 plus 2. First 2 is it is conjugacy class of I. Second 2 is conjugacy class of J. Third 2 is conjugacy class of K. Okay. This is the classification of keywords. Do you understand how we are calculating this classification?
Sir, please repeat one.
Yes.
Uh,
So its center is of order 2, right?
mm,
Now I, j, k, and plus and minus I, minus j, minus k are outside the center. Okay. So the class of, I mean, so in the class equation, what are the other factors? The conjugacy, I mean, number of elements of conjugacy class. Okay. So, and the conjugacy class is its number of elements is equal to the order of G by order of its centralizer, right? Now, if take it, if now since I does not belongs to Z of Q8, so its centralizer should contain Z of Q8 strictly. I mean, Z of Q8 should be proper subgroup of centralizer. Okay, so order of centralizer either 4 or 8. Okay, now order of centralizer cannot be 8, because if order of centralizer equal to 8, then centralizer of I equal to full Q8. So this implies I belongs to center of Q8, but that is not the case. So order of centralizer has to be equal to 4. So this implies order of its conjugacy class is equal to 2. So that's why order of conjugacy class is 2 for I. And similarly, order of conjugacy class of J, order of conjugacy class of K is equal to 2. Okay, do you understand?
yes, yes.
So, so what is class equation of Z4? Is what is class equation of Z4? Uh, Zestfood is already a billion, right? So its classification is 4 equal to 4 because it's already a billion. Understand? You understand the point that it is already a billion, so classification 4 equal to 4.
Yes.
Okay. So okay. So today time. Okay,
Sir,
sorry.
which book should we read for semi-direct product? I have not read yet semi-direct product or simple group, solvable group, etc. Or etc.
Okay. One second. So you can go with the Galleon. There is one book Galleon.
Uh, yes,
Yes, and
and
there is another book Heartstein.
Hardstein. Okay.
Yes, I could not spell. I could not pronounce it properly.
Mm,
And you obviously know about Amit, right?
mm,
So mostly Galleon will solve most of the things. I
okay.
mean Galleon. I mean Galleon is much better. Galleon is a better choice for I think.
First
So
time.
no, Galleon.
Mm.
I mean you can. Yeah, I mean you can go through Heartstein. I mean if you feel fine with that book, then it's okay.
I mean, when as a first time reader, Galleon should be proper.
As a first time reader, yes, yes. As a first time reader, Galleon is fine, perfectly fine.
Sir, which topic are actually group theory? In group theory, I have enrolled in also a course in Galois theory.
Yes,
So where so they are from here which topic are should include in this Galois theory group which
I mean,
which
in
part of
group,
group theory is one
no,
use.
Gallo theory is purely separate thing. I mean, it includes some small portion of group theory rarely. I mean, it's mostly um, involves field theory. Okay, it rarely involves group theory except one or two.
Solvable group or finitely
Yes,
generated abelian group etc.
finite abelian groups comes under module.
Yes. Okay, okay.
Okay, and solvable groups is a part of group theory, not the part of Gallo theory.
Okay, okay,
Okay.
okay. Which question you have used in this class? Can it be possible to form in a PDF form in
Yes, I have uploaded this lecture notes in slide format in Google site, right?
uh, at
I
least
mean,
question solution are to discussed in class. Okay,
yes, yes.
solution is not possible. At least question
Okay,
and some
okay,
type
okay,
of some
okay.
similar type of question there for practice purpose.
Okay, I shall. Yeah, okay, okay. I will look at it and possibly in the next class session I will let you. Okay.
Okay, okay, sir.
Yeah.
Sir, please share your email for any query regarding this.
You can. There is. Oh, by the way, please. Okay. Please give your attendance by clicking on the submit the Google form. Everybody please give the attendance. Okay, so the thing is there is one announcement portal in that swam, right? I mean there is a swam in that there's one announcement portal, correct? Sorry, there is one question asking portal in the swam website, right? Correct? Yeah, it's from okay, let me open it the website actually. Yeah, there is one question asking portal. You can ask the question here, and you will get the answer soon. Okay, understand? Okay, so okay, so let's stop here. We shall meet on the next Friday. Thank you. Okay, so I'm leaving the call. Please share your